So, well, thanks for everyone for joining. So this is actually, I mean, the title is mostly taken from a paper that we published at ITP. We sit at Alex, Chris, and Andreas. But given that we have slightly more time, I kind of wanted to give you a little bit of context what we're doing. This is mostly kind of like computer science, a computer science presentation, and maybe even not as formal as it could be. But I think you might get the connection, and maybe kind of informally, even outside of the slide, we can have a conversation on why is that relevant for mathematics, because I think it actually is. So let's see. But first I want to explain you who I am, just to kind of like also create another connection to mathematics, because when I was a PhD student, kind of this is the time where I was a PhD student, I worked on compilers. But the concept of compilers, or the way we use compilers, it's just one slide, so I don't go into it. They all come from what we call polyhedral loop optimization. So we take a loop that iterates over an iteration space, and we model that iteration space as a polyhedron. So a set of linear constraints, and then we use constraint programming to analyze the loop, reason about it, transform the program. And so there was a lot of LP or LP solving involved at that time. That's kind of where I got into compilers, and kind of one of the connections to mathematics that I have. And so one of the things we built there at that point was we built what we call an integer set library, which is a library to solve properties about press program arithmetic. So it has a little simplex solver inside, and then it identifies redundant constraints. It tries to keep the constraint set simple. And that's interesting because it's actually quite commonly used, maybe not in production compilers, but it's there are a lot of neat problems that you can express in the compiler space using this integer solutions. And then I got into, like, when I did a postdoc, I started to worry about more about the actual algorithm and the mathematical algorithms behind it. So I looked into proof certificates for like integer solutions, and then things became horribly complicated. So I moved back to normal compiler stuff. But we quite recently rebuilt this library, and so that's something that we still do quite actively. Some of the stuff we do is actually optimize this library. So this library is interesting because we only solve simple problems. So it's a couple of like 5 to 10 constraints, 3 or 4 variables. But in compilers, many of them appear very often. So our objective is to kind of solve them very fast, just because in practice they arise so often, so we need to run them very fast. So now, like, I mean, throughout this talk, I tried to make a couple of connections where I felt that it might actually be interesting to mathematics. And so when I was at ETH, I talked with some of our math department. There was a professor called Weiss Penning, who did a lot of work in that space. And so they spent a lot of their time trying to come up with really neat specialized theory statements about polyhedra, like trying to identify classes of these polyhedra that may have certain properties. And they obviously, as a proper mathematician, they used whiteboard and blackboard and paper to reason about these things. But so one thing that we never looked into, but that I would find quite interesting is, so in like medicine, or when you're in drug discovery, you try many things to find properties. And so that actually happens to be a library that for very simple cases, simple are still combinatorial many, one could explore certain properties on these polyhedra. Anyway, so that was one of the moments where I thought that is actually something that maybe mathematicians would find useful, because we keep making these little things a lot faster. They're like these Apple MacBooks have like accelerations for, like, I'm not sure if any one of you is into like AI acceleration, but a lot of these notebooks have like custom hardware to do auto products very fast. And so we just start looking into using auto products to make our library even faster, because we're careful about that in compilers. But again, there's a lot of little problems one can look at and see if these can be optimized. So I'm also like, I develop a lot of code, so I'm just really a compiler developer. I'm not a mathematician just write C++ code, and then up to 2 years ago, then I started to do a little bit of Lean. But so pretty much my entire research group just keeps presenting at this C++ compiler conferences, and then we kind of explain how to make the compilers better, which again is a case maybe not so directly relevant for the math people here, but maybe I can make the case why eventually, at least in some way, that might be relevant. So a very small example of where we use mathematics slightly more aggressively is cache modeling. And so we had a paper this year at PLDI about like cache modeling. And the problem here really is if you have a computer program, here this program, for example, and I ask you, how many cache misses does this program have? Not sure what's your, like, how many of you are actually programming? I guess most of them. Okay. So the question is you iterate over like from I to like ijk 3-dimensional over this iteration space. You see that some of that iteration space happens to be triangular. So J and I are related in a way, and you keep accessing these 2-dimensional tensors. Right. And so whenever you repeatedly access the same element, then it might happen to still be in the cache. So that might be a lot faster if you kind of access an element that has not been accessed since many iterations, then it's likely in slow memory, so you need to pull it in, right? And so the question is maybe a simpler question to ask first. Can you explain what's the computational complexity of that algorithm? What the asymptotics of that algorithm? How fast will it run? Roughly. Yeah.
Guess.
Right. It's roughly cubic. You have 3 loops, you count them, and if there is no, I mean, if none of that loop kind of trivially disappears because of some equality, it's cubic, right? So that is a very, very easy question to answer. But now you're an expert in like asymptotics program performance analysis. So tell me how many cache misses this program has. It is obvious, right? Right. So the first answer is that not enough information. So if I give you the cache size, you would certainly have guessed that it's 1.6%, right? So the point I wanted to make is, and the kind of in modern hardware, performance is mostly dominated by memory accesses. Computation is practically free. Like moving data is a thing that's really expensive. And so for a compiler, it's really useful to understand if a certain code is actually running fast or not. And that pretty much translates to figuring out for like computational kernels, does it use the memory effectively or not? And so what's interesting is it's relatively easy to figure out computation complexity, but cache modeling is by itself a relatively hard problem. So that's also the most expensive memory access. If you want to count the different cache misses, yeah, that's pretty much the numbers. But the point is that in a lot of deep learning frameworks, we want to optimize matrix multiply into slightly more complicated variants of matrix multiply that run better on a certain piece of hardware. And or we want to have a full transform, which is just a slightly more complex variant of matrix multiply. And so what the compiler really does is it looks at the individual computational kernels and keeps asking questions. Do I want to move 2 of the loops really close together? Do I want to tile them, kind of like execute the loops in smaller chunks, because that kind of these chunks fit into fast memory? And that's pretty much the thing that compilers keep asking all the time, which translates into how many cache misses does this kernel have? And so the idea here is that typically the one way to get the cache misses is just run the program. So that typically takes, in that example, 20 minutes. But if you want to do search-based exploration, really try different variants, it's preferable if this is a little bit faster. And so just to give you a little mathematical connection of how we do that, but I really don't go into detail here, is it's an idea that in these like polyhedra, you can count volumes symbolically. So counting a volume is just computing the interval from I to j, right? That if you enumerate it, it takes 3 steps, or you compute it symbolically, it's j minus I plus 1, right? And so obviously, if the interval is larger, enumerating takes more time. A symbolic computation is a lot faster. And so the interesting thing is there's an algorithm from Alexander Bavinok that allows us to do this counting symbolically. So it's one of the more mathy parts that we're using. Super cool. I don't fully understand it, so that the student who is presenting in January understands a little bit better. It's relatively complicated, but yeah, at least for me as a non-mathematician. But something that we really use, and it's really useful. I mean, it's really nice. So you can represent the entire iteration spaces and the memory behavior using polyhedra. You subtract them, you add them up, and at the end you count. Then it's a lot faster, or we can analyze a lot larger programs than before, and a lot faster than previous work. But that was just kind of a small explanation of how we use a little bit of mathematics in compilers. And next thing is that we pretty much, or one of the reasons why I started to look into interactive theorem proving is that some of our software was a little bit buggy. It was mostly okay, but it became quite subtle. And so, yeah, doesn't, if you want, and that's maybe one of the things that I'm really interested in is really I mean, one of the things we do in compilers is we want to run it on large scale software. So, I mean, at least LLVM is probably on all of your phones. We try to optimize, Chromium, whatever, large software stacks, and so kind of a typical bug in a well, it's pretty much as severe as a bug in a mathematical proof, right? It's might not be obvious at the same time, but if you have a bug in Chromium, you ship it, and then it's the wrong bug. We try to avoid that. And so we also want to scale to kind of actual other codes that we look at day to day. And so the project I'm working on is typically it's called LLVM. It's roughly the size of Chrome on Linux. So it's one of the very, very large open source projects. And an alternative version of that project is called CompCert. I'm not sure how many of you have heard of CompCert. So CompCert is pretty much the connection of compilers and mathematics. It's I think it was early 2000 when it got started. It is an amazing project. It is a full compiler that translates C code into assembly code, and then assembly code runs. You can use it as a compiler. It does exactly what a normal compiler does, but it happens to be implemented in Coq and has a full mathematical proof associated. So this thing is bulletproof. I mean, people try to test it and break it, but until today, over the last 20 years, there's no bug found, because some of the theorem prover bugs never really translated into a bug in the actual proof. So it works. It's amazing, and it's a major achievement. Maybe the kind of proof is slightly different than you would do in mathematics, but I mean the concepts, proof style might be different, but in the end, it's a full mathematical proof, which is amazing because the thing is actually bug free, so it can be trusted to almost maximal level, but kind of I'm coming from these large scale open source projects, and from our perspective, we want to build compilers that make software run fast, right? I love mathematics. It's beautiful. I'm not very good at it, but I can see the joy in it. But kind of for the general developer experience, doing mathematics really gets in our way, massively in our way. It's 2 to 3 orders of magnitude slower to build something maybe 4, like CompCert, than actually building the compiler that they run our, I don't know, deep learning software stack today. And the result is that CompCert is kind of a very tiny community of brave idealists, or rather people who identified that maybe building software for planes that don't shouldn't crash is kind of a niche that is really interesting, but it's not shipped on most of your phones. So if you look at kind of the development of the different projects and check that also the y-axis is actually different, CompCert is pretty much doing like 5 contributions whenever like people have time. And so Xavier, who started the project, is still one of the 3 or 4 really active maintainers here. And I mean, the LLVM community, we have hundreds of commits a day. Things get in our way, right? And so then there was this moment where my little like polyhedral library was buggy, and so I kind of had this maybe unrealistic dream developing that I like CompCert in a way, but kind of from my perspective as not someone who's not a math expert, I was wondering, how can I make it? Can I use it in a way, also in a way that's compatible with my community? I mean, without running into the issue that's actually quite slow to use it, right? And so another way to say that is, if you choose a normal CompCert style verification approach, you'll pretty much all the time play catch up by design. Your proofs are harder, you have less people, you never really catch up with the community that builds the compilers. But what was interesting is CompCert actually started to introduce ideas into the compiler world that were beyond. CompCert introduced them before they became trendy in our community. So CompCert realized that compilers are incredibly complex things. And doing complex proofs, as far as I learned from mathematicians, people don't like complex proofs. They like to keep stuff simple, neat, and kind of nicely modularized. Like if your proof has too much state, it becomes annoying to work with. And so what CompCert did is they said, okay, I mean, in theory, I translate from C to assembly code, but that is a huge gap that is really difficult to reason about. So let's break it down into small steps where individual proofs are easier. Compilers, in theory, historically said, you know, our biggest problem is that we have many programming languages and many targets. So we just want to solve what's called an N-to-M problem. You don't want to write a new backend for every programming language. We pretty much want to share all the backends. So everything that generates code in the end of the compiler, I want to share that with all the programming languages at the front. And the solution was I put in shared representation in the middle, which everybody can use. And so you had this kind of many languages at the front, Swift, Rust, C++, many backends at the end, and everybody shares a universal abstraction. But it was very quickly clear that a single universal abstraction shared across all programming languages is the opposite of a concise, well-defined, easy to reason abstraction. And so we didn't care about proofs, but kind of, even if we want to do our transformations, it becomes a lot easier to say, you know, I want to maybe push into a vector and pop the element out. Again, that is kind of a high-level concept that's easier to reason close to the programming language with a high-level abstraction than in a compiler where all this stuff is pretty much just loads and stores and memory modifications. And so then AI happened. And people realized AI is mostly reasoning about tensors, which is yet another abstraction that doesn't really fit into a generic compiler. But where it's really useful to have for example, here, this linear algebra representation. So these are kind of some of the TensorFlow is one of these AI compiler frameworks, kind of the user-facing framework. And at some point, they want to generate fast code for your target. And so in AI compilers, what you often want to do is you want to reason about tensors. You want to find identities that a transpose of a transpose is nothing. At that level, that's relatively obvious. Deep down, like a LLVM IR, that would be really hard. And so our community naturally moves to a design that breaks stuff into very modular steps, reduces scope, makes things like reduces state or localized state, which is very similar to CompCert. So surprisingly, now we are playing catch up. So the proof community found out that this is actually quite a useful concept. And so slowly our ecosystem is moving towards that direction. And so, yeah. And then, yeah. So pretty much our quest is to find these like little villages in the compiler where there's actually already a seed of something that would facilitate proof development. Right? So because we, like as compiler community, we would not put extra effort in writing proofs. It's so much of a pain. There's, I mean, no incentive to do that. But I mean, there was an incentive that coincidentally aligns. And then we looked into Lean, and Lean, I mean, started to build a lot of knowledge about concepts, mathematical concepts that are quite useful to mathematicians. And so the question is that maybe also something that we can use as a community, because we are building something very similar for our domain, for our applications, but very disjoint from anything that happens in the formal proof community. But what you may have observed is in deep learning compilers, we worry about like how to optimize sequences of tensor operations. So we want to exploit associativity, commutativity, a lot of algebraic properties about these things. Isn't it a little bit stupid that people who have no idea about mathematics, who mostly know about hardware and loads and stores and like caches and these kind of things, now try to build a like C++ based software framework that understands the properties of tensors very well? I mean, there's kind of a mismatch in skills almost, right? I mean, it's not entirely true because we understand that like why certain properties might improve performance, but MATLAB has an enormous amount of knowledge about interesting properties, about much more than tensors, but also tensors. And yeah, so we wanted to figure out if we can exploit that. Another little village that we have in this space is called a tool called Alive. Has any one of you heard of Alive? So 1, 2, some of the people who so Alive is the tool where like it's pretty much the only success in kind of formal mathematics in compilers. And what it does, it like whenever you look into like commits into the like Alive or in the LLVM community repositories, you see this little link to Alive whenever we have people rewrites. So localized rewrites that, for example, here take a bitcast from x to int with a sign comparison, selecting if it should be positive or negative, and you realize it's in like an absolute, it's pretty much just computing the absolute value of x. And so someone, Yingwei Zheng, in January this year, figured out this is an optimization that improves performance. And typically their thought of reasoning why this person was interested in using Alive is, so I typically in this talk, I explain you that compiler developers have family and they want to have like, go for dinner, play with their kids, and they don't want to spend 2 or 3 days explaining someone. I mean, these identities are relatively simple, but they might become more complicated. And so before Alive, the typical response was, I came up with this really interesting identity. I think it makes my code faster. And then you have a week of conversation. So is there any corner case where you may have missed that this identity actually is true? And typically there was a corner case where it was not exactly what you had imagined. And so Alive is the reason we don't care too much about correctness, but with Alive, you avoid that conversation. You just copy paste the link to a tool, and it pretty much you copy paste your input, you copy paste your output, and Alive just tells you this is correct. This is a time save, right? So we are interested as a community in formal mathematics because we want to have Alive, and Alive as a tool is a way to get Alive for us, right? But that's also kind of one of these little villages that allows us to kind of sneak formal mathematics into a community that initially was really concerned about the overhead that formal mathematics introduces. So then I came back and thought, okay, I like Alive. It's a cool tool. Many years before I started with this project, I already played with Lean. I pride myself of being on the first MATLAB paper, because when I scrolled as a kind of young postdoc through MATLAB, I found a typo in a comment. And so I fixed the typo, and then they just included all the contributors ever to the MATLAB repo, into their acknowledgements. And so because of, I think I actually fixed 2 typos. I had an early association with MATLAB, and I mean also went for some of their meetings. But so I knew Lean and knew MATLAB, and I said, can we do something like CompCert, but kind of using the ideas of Alive, to sneak. So Alive is based on an SMT solver, which is an automatic reasoning engine, but it's also implemented in C++. So it can be quite buggy. And so I wanted to have kind of a Lean level assurance that all these little rewrites are actually correct. And yeah, then we pretty much go through a couple of things that we proved around, like on the way of implementing something like Alive using Lean. So just to understand a little like what we actually work on, this is kind of the general structure of the compiler as we work with. So we have here name of an operation, an addition with a namespace in front. It may take 2 arguments, and then it has a little type signature. So that's mostly a structural property of these operations, and we just kind of chain them together in a sequence, and then we want to have, we might want to reorder or change the sequence to be faster, better, or maybe just different. So the first thing was we were trying to encode this sequence into Lean, just modeling kind of the structure of these expressions. So it's just an inductive expression, taking an argument and taking, for example, the output type here. But then we kind of like, I worked with Siddharth on this, and he got really excited. And we also had the idea that kind of our frameworks in general are parametric over the actual domain of reasoning. So we thought it's a really good idea to encode whatever we have generic over the domain of reasoning. So that comes a little bit later, but so this is the individual operation, and then this inductive type com is pretty much just creates a list of operations in sequence. And so, but what we did is kind of went a little bit overboard and kind of heavily dependently typed everything, which in some ways is quite nice. In particularly, it really is incredibly useful to give the Lean community interesting test cases about areas where Lean might not be as fast as it could be. Yeah. And then what we wanted to model Alive, we went a little bit overboard in Lean and wrote a full parser of MLIR, or like 95% parser of MLIR. So you can take whatever code we have in our compiler word, you copy paste it into Lean, and then there's a lot of meta programming behind the scene that pretty much turns that into a proof application. So the syntax of MLIR is not particularly complicated, but it kind of has a long tail of special cases. So yeah, we don't support the full. Someone I had that conversation recently told me it's not a long tail if it's infinite. So because it's an open ecosystem, I mean, I don't think we can claim we ever close it, but we support the basic structures. It's quite a fun exercise in terms of Lean meta programming, how to do that. Again, wonderful source of test cases for the Lean community, where the Lean meta programming might not scale as well. But then we can build this workflow of just copying before and after compiler programs into Lean, and then we can state a property about what we call a peephole rewrite, which says if you take a left-hand side and a right-hand side, and you give a proof of correctness, then you know this local rewrite is correct, which is pretty much what Alive does. And then we wrote a lot of tactics that kind of get rid of all our like compiler boilerplate and leaves us with, at this level, we pretty much just have a BitVector level theorem. So BitVector is just a list of Boolean values of a fixed width typically. So computers work with 32 bits, and then you reason about 32 bits. For example, that a plus 0 equals a, right? And then we have proof automation that in the best case just proves that this is true, right? So in that case, here is just a neutral element, so it's obviously true. Yeah, and so we had to implement this peephole rewrite. Takes 2 programs that pretty much correspond then to these operations. Yeah, and here, this what's sitting here is a lot more dependent typing to make it generic over the domain of reasoning. So in our little framework, we can declare different compiler IRs. So a simple one with just integers, which happen to be 32-bit bit vectors, addition and a constant. We can declare the signatures of the 2 functions and their types. And then we can give them semantics by pretty much mapping to the corresponding lean types. And so in one way, that is, I mean, just a description of what we did. In one way, I think that's also kind of the interface where we as a compiler community, we really just copy paste our source code. And what we get is thousands of bit vector problems that we are not sure how to solve. So obviously the hope is that if we create problems, other people might be like looking for problems to solve, right? Yeah. Let's see how much of this. There's a lot more dependent typing here. What's actually interesting is we also proved the rewrite theorem, which states that if you have a peephole rewrite and you apply it in an arbitrary program, and we have this rewrite peephole function, then pretty much wherever you apply your rewrite, the overall program will not change semantic wise. And that is cool because that's what actually happens in a compiler, right? We are not just want to know locally that the peephole rewrite is correct. What the compiler actually does, it has a huge collection of these rewrites, and then it keeps looking for places to apply them and applies them wherever they match, right? And so in a way, this is obviously not all that a compiler does, but kind of, from my rough estimate, I think 10% of what compilers do is just this, right? And so initially when I said that I find CompCert amazing, but CompCert doesn't scale. If you really want to have an end-to-end proof, this is really hard. But I think identifying these 5 or 10% is uniform or homogeneous enough that if you write good proof automation for that, you pretty much get the benefits that Alive offers in terms of productivity, and you might actually not need to play catch up. I mean, there's some information about like how we implement it in Lean. So there's this data structure called zippers that allows us to represent this list of let bindings. Then we can choose an insert location, kind of split it into pieces. Yeah, and keep rewriting at these different places. So that's the point in the program we want to rewrite. And then we have, I mean, theorems about our zippers that allow us to do the rewrite. Well, like about the insertion in particular. Again, a lot of dependent typing. But pretty much what really the takeaway is from our perspective, and I mean, kind of that stretches my knowledge of interactive theme proof, but Chris Youth, one of the former MATLAB developers, worked with us and said that quite good in that. So it's just that they wrote these proofs, and now we have an end-to-end proof, which I'm quite confident, and we have a little compiler in Lean that does 5%, 3% of what the algorithm community typically does. What we also do is kind of towards the quest of going towards like structuring the IRs more in LVM is that LVM gained explicit loops. So the syntax is very verbose, but pretty much we know say explicitly like there are loops in our IR, which in functional programming corresponds to a fold or something. And that is interesting because historically our representations were very much inspired by the actual hardware, where you typically just have a program counter that jumps to arbitrary places in memory and then does arbitrary operations. which is very, very unstructured. And again, very stateful to reason about when you prove things. Having explicit loops is a lot more functional, a lot more closer to the actual mathematics. And so yeah, we have little support for that as well to be able to prove properties about simple properties about loops. Then there's entire chaos in the LLVM ecosystem that I guess normal mathematicians might not worry too much about. So C as a programming language has this concept of undefined behavior. So whenever you have an addition and the result doesn't fit into 32-bit, the result in LLVM then is undefined. So the compiler can do whatever it wants, which is for performance optimization is really useful, but it makes reasoning slightly harder. In a kind of in a mathematical way, you can express it often as a monad, but in practice, kind of the actual semantics are. I mean, there's a list of papers that model the precise semantics. It gets a little bit involved, so we tested for the subset of the semantics that we model. We tested them, and they seem to work. Yeah, and then maybe the thing that gets us more towards actually like decision procedures and mathematics. So we started by trying to prove a couple of rewrites. At that point, we were like proved 67 of 93 of our like little BitVector theorems. And on the quest to do that, we built proof automation. Proof automation for very specific classes of BitVector statements. So for example, if you have element-wise and or XOR, there's a relatively simple proof using extensionality to prove them. There are ring identities where you can find the normal form, and then you compare the normal forms. And so that's something that also exists in Lean meanwhile. And then we, for certain classes of Presper arithmetic with like bitwise operations, you can turn them into an automata, and then you do automata reasoning to prove these kind of identities. So for these classes of problems, Lean now has quite good support in our personal repository for doing proofs that are generic over the bit width. And then it has, meanwhile, and that's actually quite cool, a formally verified bit blaster. So for anything that is fixed bit width, within these three classes and beyond, like addition, multiplication, division as well, Lean can formally prove fully automatically that these identities are true. And because I mean, it's a bit blaster, so it translates all of that into a subproblem. And because the domain of reasoning is finite, it's guaranteed to give you a solution, assuming no bugs and infinite memory, but in time. But and this is really cool. So we helped with like developing the BitVector theory and contributed some of the bit blasting reductions. The actual BV decide work was done by the Lean FAO, in particular Henrik, who was leading that development. So how that tool works, just to give you a little bit of an idea, we have kind of the BitVector theory where we have symbolic rewrites, where you can simplify expressions. And then at some point, you turn a specific subset of the BitVector theory into what's called an AND inverter graph. So just simple logic gates, which again, you turn into a subproblem, and then you take one of the state-of-the-art SAT solvers, solve the problem, get a proof certificate that the solution is correct, have a verified checker that this solution is correct, and all of that what is green here is all formally proven in Lean. So you don't actually need to validate any of the steps. You can just run them after, because you have proven them in all generality. So the only thing that you actually computationally then need to run is either applying these theorems or checking in the end. And so Siddha did a lot of the proofs on the division or on these circuits. And so what's actually quite cool is that now initially when we started manually, we proved like our 67 statements. And so with BV decide, we can now prove 5,000 of the rewrites in LLVM. And because they're relatively small and local, kind of here the cost of calling out to an external solver, which is BitWhistler, which is the fastest kind of non verified solver in this space. Is mostly dominated by just calling out to the solver. So we are very similar in performance. Like this PVT side tactic is very similar in performance and actually can solve large parts of kind of the rewrites we have in our compilers. Which is cool because now kind of this little village of formal methods and then the compiler community kind of took a hold. And I think we start to use formal mathematics to some degree in the compiler world. So we didn't find any bugs because our live already, existed beforehand. But yeah, they are real compiler transformations and quite a lot of them. So that's nice. There's one example that I wanted to show that might be interesting for mathematicians as well. So there's this concept of fully homomorphic encryption. Not sure if any one of you knows that. So the idea is you have like your health data on your cell phone and you don't want anyone to see it, so you encrypt it, right? So it's private, but then you have maybe someone in the cloud who has really interesting computational capabilities. So you want them to do something with your data. So you send them the encrypted data and tell them, please do something on my data. So with fully homomorphic encryption, they can actually do something on your data. They send you back the result without ever having decrypted the data. And then you decrypt it and you get the result. So that is a really cool thing. I think when it initially, like early 2000s, when this concept was introduced, kind of the performance overhead of doing it was, what's your guess?
More exponential.
So a rough estimate was like kind of 7 to 10 orders of magnitude more to actually compute an addition. And I mean, the reason is it's quite complex. So what you see here is a little bit of the mathlib definition of some of the basic data types. So it's relatively high degree polynomials over which you reason, and pretty much the entire computation happens in these high degree polynomials, where you add a lot of noise into the polynomials, and then there are some interesting mathematical statements that tell you if you have the key, then you kind of can separate the noise from the actual data, and if you don't have the key, it just looks like noise. But so there's a compiler for fully homomorphic encryption that contains a couple of operations on these polynomials, and so even though it's not computable in MATLAB, you can still state the semantics of the individual operations and start reasoning about them, proving identities, which at that point, at least for me, makes really the point, kind of as compiler developers, it's really unrealistic that we build in C++ kind of a theory of high degree polynomials just to optimize our like fully homomorphic encryption compiler. It's I mean, not just unlikely, I think it's literally impossible. And so connecting here to MATLAB is actually really cool. Yeah. Let's maybe go a little bit. Yeah, we have a lot of a couple of meta-theoretic reasonings. So like if you want to optimize your program without actually knowing what the semantics of the operations are, just based on the structure, you might know that certain operations are dead, or that certain sub-expressions are equivalent. And so we have meta-theoretic statements to perform these optimizations. We can model a little bit side effects, but yeah, we only wanted to show that we can model side effects. The only thing that we actually do is look at the side effect-free fragment that we can turn into a BitVector expression or a polynomial, and then reason at the kind of expression level. Now, I want to very briefly explain. So I told you a little bit what we do on the formal verification side. I want to give you like a 3-slide sneak preview in some of the other things we're doing. So one of the things we are doing is we build hardware compilers. So compilers that take a hardware description language like Verilog and build a chip out of them. So hardware compilation is very similar to software compilation. Instead of C or C++, you have a language called Verilog, which describes what the hardware does. You may have a couple of other high-level languages that in practice all map to Verilog. So the hardware ecosystem, if you ask anyone producing a chip, they pretty much write Verilog. That's the thing. There's in Europe in particular, VHDL was an alternative that was popular at some point. In practice, it's Verilog. And so there are different tools that exist in the hardware world to simulate your hardware, to synthesize your hardware, to prove equivalence between different pieces of hardware and to verify them. And interestingly, actually, the hardware world is probably one of the worlds where formal methods are really, really interesting, because kind of what I heard is a rough estimate of the cost of producing a chip, like easily more than 50%, 70% is really just validating the design. It's like creating the chip is relatively easy compared to making sure that when you spend millions of dollars or pounds in creating the chip, that it's actually bug-free. On the other side, they mostly do testing and actually don't formally verify a lot. But most of that ecosystem is very proprietary, and so we wanted to make it open source and introduce the compiler to kind of do that. If you want to see how the compiler looks like, so there's a little bit of Verilog here at the top, and this is just a lot of compiler IR at the bottom. The main takeaway is that, for example, here in that case, what you actually want to do in a hardware compiler very often is, and this is a little bit of a painful story, but hardware design. So Verilog is actually not a hardware design language, which is really weird because it's the language that's used for hardware design. But Verilog actually is a hardware simulation language. So it's mostly like initially the objective was to simulate hardware behavior and kind of, because of that, a lot of Verilog is actually imperative code that takes runtime choices and does something. And this is really useful to describe some things, and in particular to test hardware. But when you actually want to ship hardware, you don't want to have runtime choices where you dynamically do something left and right, but you want something that you can lay out on a chip and that doesn't change, right? You want something that you can burn on a chip. And so one of the things you want to do is get rid of all these control flow branches. And so you can actually use big classical compiler transformations to kind of restructure the code to eventually kind of get straight line code that you can burn on a chip. That's now entire like software ecosystem. There's a little bit of our original LLHD there. There's a simulator there. But so I guess one of the other takeaways is like there's not just C++ compilers, but a lot more compilers what we're building. And hardware compilers, actually, very large bit vectors are very common, or at least not unusual. So for example, some of BVB side, which works well for like 32-bit, and if you don't have divisions, it works also for 64-bit. So getting proof automation for arbitrary bit width is actually quite interesting. There's a playground where you can try our like lean MLIR stuff, and yeah, that's pretty much what I have slides for. I think what's kind of like maybe a comment that is particularly interesting for this audience is obviously, like, I guess I didn't convince you yet that I'm the most exciting mathematician. That is probably a hard thing to do. But maybe something that I'd like to point out is that I think these bit vector problems, or in general these kind of like large data sets of problems, is actually an interesting domain that maybe that like typical working mathematician is not spending plenty of time looking at I mean, this particular domain. But it is interesting because it's, I'm not sure, I mean, it's just a kind of intuition of mine. It is a domain where like there's a lot of data that is both not completely homogeneous. So the problems are not trivial. Like, I mean, I'm sure you will prove most BitVector identities within a day or a week, but they are not as trivial that you look at them and you can prove them immediately. And some of them are just hard, right? But at the same time, they are structured enough that you get a lot of data and a lot of examples of this domain. So if you're interested in like trying to build automated reasoning strategies, I think it's a really, I mean, very, very useful area for us at least. And I guess in Lean, there's an effort in kind of like coming from a slightly different direction on like using like automated reasoning and AI tools to kind of formalize parts of MATLAB. Or actually, like I think what is Terence Tao doing? Anyone knows that?
Yeah, so yeah, so I guess like it's sort of like a mix of like so basic objects of study of magma and like
Exactly.
integration between magmas, and then the objective is to like prove a bunch of these applications and like find
Right.
a bunch of people out
Exactly. And so I think actually like some of the BitVector proofs we are doing are kind of like a very concrete instance of a very similar kind of like structure of challenge, right? Like rather than proving in a full generality of magmas, it's a very specific instance with then, you have other properties to play around with, to exploit. But yeah, I think it was really interesting to see this effort. And so you're involved there?
What's for you? Very short.
And now it's done.
Yeah, now that I'll be like informally, there are a couple of things that we formalized, but
Right.
like informally, there are no issues.
Okay, so it's done.
So it's done. Yeah.
Excellent. So you're telling me you're like it. How long does it take?
The initial bit was like I think for a month. And I think it's taken like something like 2 months in total.
2 months in total.
Like it was like 99% done by at the end of like 3 or 4 weeks.
Oh, excellent, cool. So I mean then like I guess mid-February we are done with the BitVector stuff. Is that the timeline?
Yeah.
Because I was really struggling. So so that is interesting, right? So obviously you can make them arbitrarily large, but in practice, like the rewrites we have, they're all bounded, right? It's all like small identities. So it's no one is interested in like, I mean, it's just so what compilers do, they match for pattern and rewrite them with bigger pattern. If you come up with like a 100 megabyte pattern and try to match it and see if it appears in Chromium or whatever, it likely doesn't, right? It's not a very like it's the probability that your huge pattern applies anywhere goes towards zero, right? It's so we mostly have simple little like I mean bounded. I mean that's the definition of a people rewrite it. It's kind of rewrite in a small local context. I mean there's still a lot of variation there, but yeah. So I mean we have some ideas how to get a couple of at least one new decision procedure for the BitVectors, which we find exciting. But that will still be, I mean, so we have another like one of these automata domains that I think we can close completely, and we'll be sure that will be fast. It's actually quite cool because they're like just combining, I think like addition and bitwise operations is something that even like I think mathematicians didn't look into it too much because it's not so commonly useful, or but it's quite useful for us. But afterwards, I think there's still a lot of problems. I would actually really love to see some more automation in that space.
Yeah, sure. I'd love to chat about it.
Again?
Yeah, I'd love to chat about the
Lovely. No, I'm really excited. I mean, yeah, cool. That's it so far.
Okay, I feel like we've already shifted into the question.
Exactly. All right, let's start with the first.
Those that are in do those syntactic rewrites. Like, oh, I see something that matches the bottom of the rewrite. Is there some sort of other some more semantic approaches to optimizations?
What do you mean by semantic approaches?
I have no idea. But I'm guessing all optimization in the compiler may not only be done through rewriting already known methods.
No, obviously, like I mean, they're but I mean that doesn't. I'm not sure that's that it counts for like the difference between semantic and syntactic. I mean, but like the rewrites is pretty much you match for a pattern and you do that, and I would my understanding is maybe 10% of our code base does like either this kind of syntactic matches or maybe slightly more semantic meaningful, where you kind of do a little data flow analysis to for example prove that certain bits are now like 1 or 0, and then you like take that into account. And then I mean there's an entire like 80% of where you actually look at the like data structure of the program and then do like a running non-trivial algorithm to compute some properties. I mean that's the hard stuff. Yeah, like but that's the stuff that's really hard to mechanize.
Yes, my question is, in the long term, are there any forms that you may be able to formalize such complex documentations in
I mean, like, I mean, people in CompCert did it, right? You can mechanize all of them. It's just, I mean,
points of CompCert or probably normal components?
I mean, so the thing is that a lot of these like really specialized optimization, complex optimization, they don't fire that often. Right? So in terms of these things, they actually like, I mean, because they exist, I mean, it's actually relatively easy to match for a pattern and other stuff. I mean, in very specific cases, they work really well, but they are not incredibly common. So CompCert is not actually too far off from like for certain workloads, just because some workloads, like so, like actually, for example, Chrome or whatever, if programs are sufficiently unstructured, then these small things still fire, but like big refactorings are also for compiler quite hard then.
Yeah.
And so, I mean, or the other example that maybe is closer to your kind of heart, Lean is using LLVM as a backend, right?
Yeah.
I think that's pretty much the only thing that will fire Lean. There's like most of LLVM's optimizations for Lean are not meaningful. Because what LLVM sees for Lean is it's this kind of a void pointer that carries no data type, and it's pretty much just loading and moving like void objects. And so does the LLVM vectorizer trigger on void objects where you don't understand aliasing properties? No. Does the LLVM loop optimizer optimize like Lean functions? No. Right. So most of the things that like LLVM would do, they don't apply to Lean. So the only thing that applies to Lean is there's a subset of like basic Lean types, integer types, which are explicitly exposed to LLVM, and then LLVM might be able to fold them into smaller things. But yeah, LLVM doesn't do anything useful for Lean. I mean, except actually making it run, but performance-wise, yeah.
What about optimization, or is it just this LLVM just suck at that? Because I think LLVM is a Haskell in some.
So LLVM is not a Haskell backend. There exists an LLVM-based.
Didn't you say compile with LLVM?
Oh, C I think is the default backend. There exists an LLVM backend for Haskell. I don't think it's, or maybe it's actually, it's quite solid. I mean, we chatted with Simon Pete Jones a little bit about it. But yeah, anyway, so you asked about two things like loop optimization. I don't think they may fire a lot. Tailcode optimization is something that, I mean, it's useful for a language like Lean.
Yeah.
And yeah, sure.
I mean, because like usually what you try to like reduce short programs and compare. So you're just not doing that much.
I mean, like, but there's not a lot you can do, right? I mean, you can, when you do the tailcode transformation, it's useful. LLVM has guaranteed tailcode optimization, which is useful. So that's one, like, that is one of the like non-local transformation that LLVM does that is actually quite meaningful to Lean. That is true, yeah. So that's like, I mean, you pick the one, I mean, that is one of the things that actually Lean, I think, in very rare cases benefits, but yeah, there was a very concrete bug where, well, like you need tailcode elimination.
I think there's a few issues where people claim that foundation were explicitly not configuring seemingly recursive function indeed, so I'm not certain how smart LLVM manages to be on the code specifically.
Yeah, I mean, not sure how smart it is, but it has guaranteed tailcode elimination. So I guess that means it should fire. Yeah.
When you were designing the syntax for MLIR, why did you pick to intrinsically type it, like intrinsically carry this context around, rather than, for example, tracking that side as a proof? Some design, but like having implemented now, lots of semantics and Lean, often intrinsic, sometimes extrinsic.
Yeah.
Most of the times extrinsic. Intrinsic is just often so much more painful.
Yeah, well, it definitely is. Yeah. I mean, I'm not sure that was a good choice. I think the reason was that some of my students were quite excited about dependent typing, which is something that sometimes happens. Exactly. So I mean, one thing, I mean, if you want to have a really cool formally verified compiler, I mean, Lean MLIR is definitely high up on the coolness spec. I mean, the hour dependent typing is, I mean, it's actually really cool. And I mean, it's actually really cool. I mean, I mean, I agree with the sense of like maintaining software, but I mean, a lot of things now, like, I mean, it was painful to get it right, but now, I mean, actually, I mean, it's really nice. You write your semantics, you mean, you immediately know if you have one argument too much, I mean, like, I mean, there are a lot of things that then happen to work. And again, I mean, it was actually quite cool to see, I mean, with a lot of bravery, they kind of, my students got these proofs through and made them work. And it was nice to see how kind of Lean evolved over the last year or two. So when we started doing that, I mean, one thing that was maybe not very clever is doing dependent typing at the beginning at all. But the second thing that was not very clever, doing it when Lean was didn't have support from the Lean FO so much, and this was, I mean, the kind of code we wrote is definitely not something that is typically for Mathlab. So Lean was not particularly polished in that space. And so it was really nice to actually see like as the FO polished Lean and like added support for like better support for mutuals and like that Joachim added. I mean, every time, like I always like every month we updated Lean, or like daily we update Lean, but like every month there was a major patch where we realized, oh nice. So we really like tested with some of the new features and found some bugs, but also like just saw the development flow to become a lot better.